Hello, today we'll talk about power of a reflecting surface, power of a lens, power of a mirror, properties of power, and we'll use this power method to solve few problems in optics. Right, so what is power? When we are discussing lens, we said that power is nothing but 1 by the focal length, right? So power, when you want to say, is basically an ability of an optical device, let it be lens, mirror, or anything, to sort of bend the ray of light, right? So if the ray of light is getting bent more, right? So suppose this is our optical system, right? This is the lens or something. The ray of light is coming like this. It is getting bent like this, right? At a particular distance. And with the second optical system, the ray of light is bending like this. So which has more power, right? So the more bending is happening, that is the more powerful. Okay. So it's an ability or property of the optical system to bend the light. Okay. So the more bending, more powerful. Okay. So as you can see, this is the focal length f1, this is the focal length f2. Here the f2 is bigger but the power is less. Here the focal length is less and hence the power is more because it is inversely proportional. Now we'll use this video to sort of devise equations and define power for different surfaces and dive down into its properties so that we can use that to solve many problems pretty easily, right? So to get started, let's talk about a spherical surface. Okay, so here is the surface, here the refractive index is n1, here it is n2, and the ray of light sort of coming like this and the sort of getting bent. Okay, now in this case, let's say the radius of curvature of this refracting surface is given to be r. Okay, then the power of this surface is defined as n2, which is the second refractive index or refracting surface index, minus the first index in which this surface is, divided by r with proper sign convention. Okay, so here power P is in diopters, which is m to the power minus 1, right, in meters. N2 is the refractive index of the refracting surface, and N1 is the refractive index in which this surface is. Usually it could be air, but it could be anything, and that's why we are considering a very general equation here, which is N1 in this case. So now, and R is basically the radius of curvature with proper signs as per sign convention. Okay, so our sign convention which we are using is basically the Cartesian one, right? So here is a point O, and anything the ray of light is coming like this, on this side is positive and this side is negative. Now for this surface, basically the radius is falling on this side, so the R is positive. And if we have a surface like this, right, then the R will be negative. So we have to take care of all that, which is N1, right, from the direction the ray is coming, and which is N2. And when we do that, basically we will be able to solve any problem, and we'll be able to find the power using this simple equation which I have written over here, which is power is equal to N2 minus N1 by R. So let's do an example which will make it very, very clear. Now here is an example which says end of a long glass rod of refractive index 3 by 2 is polished with a spherical curve that has a radius of 5 centimeters. Calculate the power of the surface. It is not saying is it concave or convex, so we are going to assume both the cases, right? So first let's assume that it is a concave, and here is our glass rod, and we have carved out a surface like that, and it is given that the radius of curvature C or R here is 5 centimeters. Okay, so this is C. Now this is going to be our origin where the reflection will happen. This side N1 is air, so 1, and here N2, right? So left hand side is N1 and it is 3 by 2 which is equal to 1.5. And now we have to find the power. The power is n2 minus n1 divided by r, and r in this case, because it is lying on this side, r is going to be minus 5 centimeters, which is equal to minus 0.05 meters, right? We said that we have to take it in meter. Now n2 is 1.5 minus 1 divided by minus 0.05, and it will come out to be minus 10 diopters. Okay, now if we, instead of assuming it sort of concave, basically we can assume also that it is a convex. So here's our rod and here's our surface in that case. Okay, and this r is given. Now the ray of light is again coming from this side, so this is n1 is equal to 1 and n2 is equal to 3 by 2 is 1.5, and this time around the r is falling on this side, right, this side. So r is positive 0.05 meters, like we said. Then we again calculate the power of this surface. So n2, which is 1.5 minus 1 divided by r, this time it is positive 0.05 m, and it turns out to be plus 10 diopters, which means that when we have a sort of convex surface, right, the power is positive, and we have a concave surface, the power is negative. Okay, so we can write that down. For the concave surface, power is negative. For a convex surface, power is positive. Okay, now how about we sort of turn this around and see what happens if the power changes, right? So we are going to turn this rod around and again calculate the same thing, right? So let's turn the first rod around. So basically we have now the rod is on this side, right, and the concave surface is on this side, right, and now here is n is equal to 1.5. now n2 is equal to 1, and here is the origin, and now the r is falling on this side, so r is positive. Okay, so r is plus 0.05, and we can fit that again in the power equation. P is going to be now equal to n2, which is 1, minus 1.5, and this r is positive, so 0.05, and it will turn out to be minus 10 diopter, exactly same as what we got there, right? Now let's turn this one around and see what happens. So now we have this rod. Now the surface is on this side. Here n1 is 1.5 and n is equal to 1. Okay, and now the r is on this side, right, which is the negative side. So r is going to be minus 0.05. When you put that in, what we'll get into the equation, which is this is L2, right, N2 minus N1 divided by R, and that is going to be 1 minus 1.5 divided by minus 0.05, minus minus will cut, right, so it will be 0.50 by 0.05, and that will be plus 10 diopters. Okay, exactly as the same as the last one which we got here. What it means is that the surface only has one power, its orientation does not matter. Okay, so we are going to write that down, the concept. Surfaces have only one power independent of its orientation, and this is what we expect in physics, right? The law has to work in both the direction, right? So we can find the power, and then we can use all that, right? Now let's try and use this basically to use in the lens, right? So what happens in case of a lens? So when we have a lens, right? So we have, let's say we have this convex lens, right? And it is in a medium, let's say, and not on this side, okay? And here the refractive index of the lens is NL, okay? And now here let's try to find out the power for this, right? So first we have to find the power for this one, okay? Let's say the radius of curvature for this one is R1, and for this side is R2, okay? So let's find the power for the surface number 1, which will be NL, which is the, so we said N2 minus N1 by R, right? So here we'll write it down for the first surface, surface number 1. N2 is equal to NL, okay? And N1 is going to be equal to N0 in the medium which the lens is, right? And R1 is positive, so R is equal to positive R1, and so we can write the power 1 for the surface number 1, same equation, power for the surface number 1, P1 is going to be NL minus N0 divided by R1, okay? Now let's find the power for the surface number 2, okay? Now here it is. Now the N1 for the surface number 2, N1 is now going to be equal to NL, okay? And N2 this side is going to be equal to N0, and the radius, right, it is going to fall on the negative side, right? So the R is going to be minus R2, hence the power for the surface 2 is going to be N2, which is N0 minus NL divided by minus R, okay? And now you can simply add this up to find the total power for the lens. So that's the beauty of power, right? So power has an additive property, okay? So for the power for the whole lens is going to be equal to P1 plus P2, right? So let's add that up. So we have NL minus N0 divided by R1 plus, with this minus sign, right? So it will reverse again, NL minus N0 by R. So R2. So this will be it will be minus, okay? Take out the NL minus N0 outside, and then we have 1 by R1 minus 1 by R2, and that is going to the power. And if you remember, this is what we derived as a lens maker equation, right? So the lens maker equation, we say the focal length 1 by F is equal to NL minus N0, right? So this is the lens maker formula, and this is exactly what we arrived using the power equation, right? So power has this additive property, right? So let's take few examples to clear this up. Now we have a bioconvex lens made of glass, which is a refractive index of 1.49, right? And a surface with a radius of curvature 40 and 20 centimeter. Calculate the surface and lens power, okay? So we have this one. Now R1 is 40, R2 is 20, and N is 1.49 or 1.5, or we can write it as 3 by 2, okay? Now let's calculate the power of this one, okay? So power is going to be N2, which is 1.5, it's in air, divided by R. R1 falls on the positive side, so which is 40 centimeters or 0.4 meters. This is going to be 0.5 divided by 0.4. Okay. Diopters. This is our P1, and the P2 will be again here. Now the N1 is 1.5 and the N2 on the other side is 1. Okay, it's a reverse one. And then R2 is on the negative side, so it is minus 0.2 meters. Okay, and the power is going to be N2 minus N1 by R, and this is going to be 1 minus 1.5 divided by minus 0.2, and this is going to be minus 0.5 divided by minus 0.2, and that is equal to 0.5 by 0.2. We can simply add that up to find the power of the lens. So 0.5 by 0.4 plus 0.5 by 0.2, and you can do the maths and you will be able to find a positive power. Okay, so this is for the convex lens. Let's suppose that this lens is concave, right? Then what will happen? So taking a similar example, basically here now the lens is say bioconcave, and basically now the R1 is 40 centimeters and R2 is 20 centimeters, and this one N of the lens is 3 by 2, okay, or 1.5. Now let's find the power for the surface number 1. Surface number 1, we are going to write it down first. N1, which is in the air, is 1. N2 is going to be 1.5, and the R in negative direction is minus 0.4, and the power 1 will be N2 minus N1 by R. This one is going to be 1.5 minus 1 divided by minus 0.4, and roughly it's going to be 1.2, right? And this is going to be negative. Okay, now let's find the power for the second surface here. Now here N1 is going to be 1.5, right, moving from this direction to this direction. N2 is air, so 1. Now the radius is on the positive side, the R is going to be plus 0.2 meter, and the power P2 for the surface N2 minus N1 by R, and this is going to be 1 minus 1.5 divided by 0.2, and that is roughly 2.45 negative. And when we add that up, basically you have minus 3.68 diopter P1 plus P2. Okay, and as it is negative, no, we know that it is a concave lens, right? So for the convex lens, the power is positive because it converges the rays, so it's an ability to converge. The diverging lens or concave lens, concave lens, power is negative because sort of diverges, right? So it's a disability to sort of put it there, right? So now with that, you can also sort of try for this example, right, switch the curvature of the lens and see what happens. Okay, now so instead of saying that, you know, let's do it on this side. So instead of saying that the first one had a curvature of 40, let's say this one has a curvature of 20, right? So this has a curvature of 20 centimeters, and this has a curvature of 40 centimeters, right? And then this is 1.5, and then we can calculate the power for the surface number 1, okay? And this one is going to be again N2 minus N1, 1.5 minus 1 divided by, and this is on this side, so minus 0.2, and for the second one, this side now N1 is N2 is 1, so 1 minus 1.5 divided by minus 0.4, and you will arrive at the basically the same result, right? So what it means is that whether we calculate the power using this side or that side, right, that reversibility does not matter, right? The power remains the same for the lens from both the sides, like we observed for the spherical surface, right? So that's that thing. Now let's move on to a mirror, right? Before we do that uh, problem, let's formulate our understanding, right? Now for the mirror, as you said, here is, let's say we have a mirror silvered on this surface, and now it is in refractive index n1, and let's say this side is n2. In case of refracting surface, we said the power is going to be n2 minus n1, and that will be divided by r, right? Now in case of, and we almost also said that reflection is nothing but a special case of refraction when n2 is equal to minus 1, or when the n2 has sort of a negative refractive index, so that it sort of bends the lights away, right? So we said that in the example where we have this surface and the ray of light is coming like this at an angle of incidence I, and it's getting reflected at r, but now instead of getting reflected, it's getting reflected at I, right? And we said that here is a n1 n2, and we can write the Snell's law here, which is n1 sine I is going to be equal to n2 sine r, or the reflection. Now the angle of reflection here is negative I, right? So it is n2 sine minus I, okay, which means that n1 sine I is equal to minus n2 sine I, and sine I we cut, which means that reflection is nothing but a special case where n2 is equal to n1, right? So for reflecting surfaces, right, we can simply define the power equation very simply as P is going to be n2 minus n1 by r when we substitute this, right? So let's substitute that. The minus n1 by r, this is going to be minus 2n1 by r, and we can say 2, the refractive index of the medium, divided by r with a minus sign, is what will be the power, okay, where r is the radius of curvature of reflecting surface, and nm is refractive index in which the surface is placed, right? And we have to take care of the sign convention, and then we'll be able to easily calculate that power, right? Why we are putting so much effort on the power is that power equation actually allows you to solve a lot of complex problems pretty easily. So bear with me. Let me explain this with a problem, right? A curved mirror has a power of minus 6 diopter underwater. Okay, so we have a curved mirror as a negative, right? So it is going to be a convex mirror perhaps. Okay, and it is underwater. Okay, so it is in a medium where n1 is 1.33. Okay, what is the focal length, radius, and power of the mirror in the air, right? Now we do not know the radius, right? So now when we know the power equation, right, we can say that for the power of a mirror is going to be minus 2 in the medium it is in, right, divided by the radius of curvature. Power is given, nm is given, we can easily find the radius. So let's find the radius. R is going to be equal to minus 2 into nm is 1.33, okay, divided by r, right? Now r is what we need to find out. Now the power is given to be, sorry, the p, right? So power is going to be minus 6. It is going to be minus 2 into 1.33 divided by p, which is minus 6, and minus minus will cut, and basically we get 44.33 centimeter positive, right, as we expected. On this direction this is positive, so r is equal to plus 44.3. Now we can use, now we have the information which we can write. Now we know the r, right, or the absolute value of r, and now we have to find the power of the mirror in the air. So n1 now is equal to 1, and or nm is equal to 1, and we can simply use this equation p is equal to minus 2 into 1, and we divide it by the radius, which is plus 44.33, and we'll now get a negative power of 4.51 diopter, which means that this surface is basically now acting as a curved mirror in the air, right, which is a negative power 4.51. Now let's move to our next problem, and before that, basically, as we said, that the power is basically additive, right? So additive law of power is what we wanted to discuss and write about, right? So let's do that first. We said that we have a lens, okay, surface 1 power p1, surface 2 power p2. The power of the lens is p1 plus p2, does not matter what kind of lens it is, okay. Right, of a lens. Similarly, suppose we have two lenses, right, which are in contact, okay. This lens has a power pl1 and this is a power pl2. The power for the whole optical system is in contact is going to be p1 plus p2, okay. It's p1 plus p2, right. So we have this lens like this, okay. They have three lenses, power p1, power p2, power p3, power for the system p1 plus p2 plus p3, okay. Now this for the lens. Suppose now we have a lens and a mirror combination in contact, which means that one part is silvered, okay. So now we have, let's say, a lens like this, okay, and now this part is silvered, right, and we know the power for the lens is p1 and power for the mirror is p2, okay. What will be the power for the system? Now observe carefully, when a ray of light is going to come, first is going to pass through the lens, the power is going to be equal to p1, then it will have interaction with the p2, right, and then will again pass through p1, right. So again we have to add that up, right. So it's going to be 2p1 plus p2 in this case, okay. Now if we have similarly a sort of concave surface, like we have this convex one right now, so we have concave lens, so this part is inward, power p1, this mirror is power p2, we'll write p1, right, ray of light is coming like this, then interaction at p2, and then again passes through the lens p1, this is 2p1 plus p2, right. And once we know the power, basically we know the focal length, right, and once we know the focal length, basically we can calculate the the distance of position of the image, right. So very very powerful. Let's do an example, okay. So bioconvex lens of refractive index given, right, it's a bioconvex lens, refractive index given, n is equal to 1.523, has a power of 10 diopters, right. So it's a positive convex lens. The back surface of the lens is now silvered, right. So let's silver this up. The power of the lens is plus 10, so that it can reflect the light. Now of course calculate the power of the system of lens and a mirror so formed, right. Now we do not know anything about the power of the mirror, but we know the power of the lens, right. So is there any way to sort of calculate this radius, right. If we know the radius, then we can derive the equation, because the power of this mirror is going to be minus 2 n, right, which will be the refractive index of this, divided by r, right. If we know the r, then we can find this power, okay. And if we can find the power, the whole power, the power of the system is going to be power of the mirror, sorry, power of the lens plus power of the mirror, right. P1 is given. For the PM, we know this formula is 2 by n by r, right. Now we can find PM if we know r, because n is given, right, n is given. Now, can we find this r? Yes, we can, by using the formula for the lens first, right? So for the lens, for the surface number 2, right? For the surface number 2, let's write down the power equation for the lens, right? So for the lens, for the surface number 1, for the surface number 1, yeah, we can write simply for the surface number 1 and that will do, right? This is our surface number 1. It has a radius r, right? The second is also bioconvex, so we just need to find that r, very easy. Now n1 is equal to 1, this side n2 is equal to 1.523, right? So the power for the surface, right? Now we write is equal to 1 minus 1.523, and we have to find the power of the surface one, right? Now, because this is a bioconvex lens, right, so it consists of two surfaces, and both the surfaces are equal, right, equal in radius, right? And as we said, whether we sort of turn it around, so both the surfaces will have equal power, which means the total power of the lens, right, will have power of surface number 1 plus power of surface number 2 is going to be total power of the lens, right? And this 2 is going to be equal. So power of surface number 1 is going to be equal to power of the lens divided by 2. Okay, and this is what we'll use here for the power of surface number 1, and the power of surface number 1 is now going to be equal to 10 by 2. So 1 minus 1.523, and the power of surface number 1 will be plus 10 divided by 2, and with that we'll be able to obtain sorry, this will be the radius now. Okay, so we have subtracted that equation. The r is going to be equal to minus 10.46 centimeter in this case, and basically you can simply write we now know the radius, right? So the modulus of radius is 6. Okay, centimeters. And now we can calculate the power for the mirror. Power for the mirror is going to be minus 2 into n is 1.523, and divided by, on this side it is negative sign, right? Minus 10.46, which is 0.1046 meters. Okay, so it is minus 2 into that, and basically the minus minus will cut. So now we'll have 29.12 diopter, which is the power of the mirror. The power of the system, as we said, is going to be, first the ray of light is going to come here, right? So total power of the system is power of the lens plus power of the mirror, and then it will be reflected again through the lens, power of the lens. The power of the lens here diopter. Okay, so the lens, the system is more sort of powerful than the one lens itself. Okay, now let's do the another problem. A convex lens of focal length 20 centimeter is placed on a convex mirror as shown below, right? So this is our convex lens. It's placed on a convex mirror. A parallel ray of light incident on the lens from the top get reflected by the combination and remains parallel after reflection. So ray of light coming parallel here, after passing the system, gets reflected back and remains parallel, right? Calculate the radius of curvature of the mirror. Now no information, much information is given, but just the focal length of the convex mirror here is given, right? So we can calculate. So what, let's first see what the physics is, right? So the ray of light is coming like this, getting reflected, and then again without changing any direction, right? So the system is not converging or diverging the rays, right? Which means that the power of the system is equal to 0. Okay, and we know that the power of the system is power of lens, okay, and plus the mirror, and again it is getting reflected, right? So it is going to be power of lens again, okay, 2 times the lens. So 1 time here, then the mirror, and then the lens. Okay, so 2 time power of the lens plus 1 time power of the mirror. Okay, and that is going to be equal to 0, right? So now can we calculate the power of the lens? Very easy, right? So the f is given to be 20 centimeters. So power of the lens is going to be 1 by 20, or 0.2 in this case in meters, and that is going to be 5 diopters. Okay, so now we have power of the this thing. Now can we calculate the power of the mirror using this equation? Of course we can, very easily. So we know that it is going to be 0. So the power of mirror is 2 into 5, which is 10, right? And plus PM, right? It is going to be 0. So the PM is going to be minus 10. Okay, and now can we calculate the radius of curvature using the power of the mirror equation? It is very simple, minus 2, yeah, and it is lying in the air, so 1, and divided by the PM, which is minus 10, cut, sorry. So let's write down this one, right? The PM of the this one is known, right? So then PM is going to be equal to minus, right? Minus for the mirror is going to be equal to minus n into 2, right? Minus 2n divided by r. Okay, hence this is minus 10, right? So minus minus will cut, and the r is going to be equal to n, or 2n by 10. Okay, and n is equal to 1, so r is going to be 2 by 10, right, which is 0.5, yeah, 0.5 meters, or you can say 2 by 10 is not 0.5, it's 0.2 meters, right, or 20 centimeters. Okay, so the radius of curvature in this case for the convex mirror is 20 centimeters. Okay, falling on the positive side, r is equal to 20 centimeters. So that is our answer. Think about that, how we solve the problem. We basically first wrote down the equation, and we, by physics, we said because there is no sort of convergence or divergence of the ray, which means the power is 0. So we added up the power for the system, and we make sure that we add the power for the lens twice, because the ray is passing twice through the lens, and once for the mirror. And we said that because it is 0, we can also very easily calculate the power of the convex lens, and then we plug in the numbers to get the power of the mirror. And by using this simple equation for the mirror, we were able to arrive at the radius of curvature of the convex lens, right? Now let's do another problem. Here a double convex lens is made from 2 identical watch glasses. Yes, here is the 2 identical watch glasses. We're filling the space between them with water, right? So we are filling it up with water. Water we know, then it's equal to, okay. So the power of the lens is 4D, right? So P power of this lens is given to be 4 diopters. Now similar watch glass is placed on a cylindrical container such that it forms 2 lenses. So here is our watch glass, right? So it's one watch glass, right? It's placed on a container, right? So it's making two lenses, lens A and lens B. After the space between the container and the watch glass is as well, the watch glass is filled with water. So this whole thing is filled with water, inside also, outside also. Find the power of lens B. So we just have to find the power of lens B. Now see, it is now a plane surface, right? So the ray of light coming like this straight is not going to converge or diverge, right? Which means the power of A plus power of B is going to be equal to 0. Okay, similar condition like what we used in our last example, right? So when there's no convergence or divergence of the ray, the power is 0. Okay, so now we have to find the power of lens B. So power of lens B is going to be equal to minus power of lens A, right? Now can we find the power of lens A? Yeah, it is a part of this lens, right? It is a part of this lens. And now because we are cutting this surface into two parts, and as we said, the power of this lens is sort of power of this surface and this surface, and we are taking away the half, right? So power of this lens A is nothing but the power of the convex lens divided by 2. Okay, so it is 4D divided by 2 and it is 2D. Okay, positive. And now we know the power of the lens B is going to be equal to minus 2D. Yeah, we just plug that in. The power of lens B, which we want to calculate, is minus 2 diopter. So basically, very easily we said, if you have fundamentals clear, you can very easily solve that. Otherwise, you'll get stuck finding focal length and using lens maker formula, etc., etc. We reach nowhere, right? So just recapping the power, right? So power is an important concept. So for the surface, we said power of a surface is nothing but n2 minus n1 divided by r, where n2 is the second side and n1 is the second side, sorry, for the first side, yeah. And we also said power of a lens of a surface 1 and surface 2 calculated by this formula. The power of a lens is power of surface 1 plus power of surface 2, and if we said more than one lenses, stick together, so 3 lenses here, so here is p1 plus p2 plus p3, yeah. And we said if we have a combination of sort of lens and a mirror, and the ray of light is coming like this, right? So this is the power of a lens, this is the power of a mirror. It is going to be power of a lens again for the power of mirror plus power of a lens, because the ray is sort of after reflection again traveling in the lens, right? So these are the few things we said, and we said if there is no deviation or conversion or diversion of a ray of a light, right, like this lab, the ray of light is passing straight, the power is equal to 0, right? So this is our, and we have, let's say, cut off two lenses like this. This lens number 1, this is lens number 2, then this power of this one and this one is going to be equal to 0. So we'll solve more problems related to mirrors and lenses in our next video, but this is the important concept, right? And using this, you can solve a lot of problems. If you want to watch more videos, you can go to deepdivephysics.com, where you can watch this video in a very structured playlist without any advertisement. And also, if you want some guidance, we provide one-to-one and small batches tuition. So please get in touch to get advantage of that, and we'll be happy to help.